In this lecture, we will talk about circuits that contain ideal diode, constant sources, constant independent sources, and LTI resistors. In particular, we will try to obtain the IV characteristics of one-ports that contain the components that I just listed. Okay. So, to be able to talk about today's lecture, we have to introduce a new component, a resistive component, a nonlinear resistive component, which is called a diode. Okay. Even though it's nonlinear, its analysis is quite straightforward because its nonlinearity is a very special type of nonlinearity. It's called piecewise linear nonlinearity. Okay. Now let's introduce what we mean by an ideal diode, and then we'll see how we can study the circuits that contain an ideal diode and LTI resistors and independent sources. Okay. So this is our new component that we will be working with for a while, ideal diode. Okay. So this is how we represent it on paper. Okay, this is a schematic representation of an ideal diode. Okay. So suppose that this is its voltage, and we always, regardless of the component, we always respect the passive sign convention. Therefore, its current is in this direction. Okay. Now, the IV characteristics of an ideal diode is very simple. This component behaves either like a short circuit or an open circuit. Under what conditions it behaves in such way is as follows. Okay. It behaves as a short circuit, that is, the voltage drop across its terminals is zero if the current passing through it is positive. Okay. When the current is positive. And it behaves in the other mode, the open circuit mode, I equals 0. When the voltage is negative. Okay, the voltage drop across its terminals is negative. So overall, the IV characteristics is like this. So when current is positive, okay, so current positive means we're talking about the upper half plane, okay, those are the points that correspond to positive current. The voltage is zero. Therefore, all these points on the positive vertical axis are possible operating points, and when the voltage is negative, therefore we're talking about the left half plane. Okay. When we're in the left half plane, the current is zero, it behaves as an open circuit. Therefore, all these points on the left horizontal axis are possible operating points. Okay. Note that the IV curve is not symmetric with respect to the origin. Therefore, this component is not bilateral. It means that if this is part of some circuit, okay, and that circuit operates in such a way, if you take this component out, reverse the terminals and put it back to the circuit, then it will become a completely different circuit. Okay, its operations will change, so we have to be careful about that. And also, as for non-bilateralness, here is a useful fact that we will resort to in our following analysis. Okay, let this be some resistive component. Okay, two-terminal resistive component with nodes A and B. Be an arbitrary resistor component. Okay, any one port. Now, if the IV characteristics of the component where the voltage and the current are taken in the specified polarity and specified direction, such. And for that choice of voltage and current, we have, suppose, some IV characteristics, okay, on the IV plane. Okay, so IV characteristics, okay, those are all possible operating points, let's say. Then, if you reverse the terminals, okay, this is now B, this is A, and now this time the voltage and current are from the direction of current is from B to A. Previously it was from A to B, so basically you're swapping the terminals. Then this, you can call it in a sense a new component, has the following IV characteristics. Okay. VI 0. Okay. So all we have to do is take all the operating points in this IV curve and replace them with their symmetric points with respect to the origin. Okay, so if you take all those points, the symmetric of all those points with respect to the origin, what you obtain is something like this. So all we have to do is to go from this component to that component for the IV characteristic point of view. You have to take the symmetrics of the operating points with respect to the origin. Okay. So these are reflections of each other with respect to the origin. Now, this fact will be useful in our analysis to come. Now, let's see how we can obtain IV characteristics of one ports that contain diode, okay, ideal diodes, LTI, resistors, and constant voltage sources or current sources. So series and parallel connections of diodes, LTI, resistors, and constant sources. Now, let's begin with a very simple case. A resistor and LTI resistor connected in series with a diode. And after that connection, a new one port is obtained, and now we will try to figure out IV characteristics of this new one port that contains two elements, okay, an LTI resistor and an ideal diode. Okay, so suppose this is the polarity or the voltage and direction of the current, okay, with precision VI curve. So the resistance of the resistor, let it be R, and this is the ideal diode. The direction is given as follows. So let's specify separately the voltage of the resistor and the voltage of the ideal diode. The voltage of the resistor we call V of R, and the voltage of the ideal diode in that direction, plus minus, we call V sub D. Okay, voltage of the diode. Now that we don't have to differentiate between the current of the resistor and the current of the ideal diode because they are in series, and it's the same current that visits both. Therefore, this I is both IR and ID. So we just give it as I. As for V, the overall voltage of the one port, it clearly is, because the components are in series connection, it equals the sum of voltage VR with voltage VD. Okay. Now what we're going to do to obtain the IV characteristics of this one port is we're going to plot the IV characteristics of each of those components separately, and knowing that they're connected in series, we're going to do series addition of those two separate IV characteristics. Okay? So this gives us, okay, so this is our IVD, the IV characteristics of the diode. Okay, so by definition, it's all these points. Okay, and then we have the IV characteristics of the LTI resistor. Clearly, it's by Ohm's law. VI equals R times I. Therefore, it's a line that passes through the origin, and the slope of the line is the conductance of the resistance, which is 1 over R. Okay, this and that, they're connected in series. Therefore, we're going to do series addition. Okay, and this is notation that we use to indicate series addition. Okay, this plus series addition, that equals the overall IV characteristics. Okay, now the question is how we perform this series addition. Okay, now V equals VR plus VD, clearly, because this and that, they're in series connection. So what we're going to do is we're going to add voltages. By adding voltages, I mean the following. Now, just pick a current, okay? For that current, figure out the voltage that's generated over the resistor, okay? And then figure out the current that appears across the terms of the diode, okay? And then add those two voltages, and the result is the voltage of this one port corresponding to that particular current. And then you move on to another current. You figure out the voltages separately, add those two voltages, and mark the operating point. Pick another current, take the voltage from here, take the voltage from here for that particular current, obtain the operating point, and mark the operating point on the resultant curve. Okay, and once you're done, all those operating points will make the so-called IV characteristics of this one port. Okay. Now, pick a current, for instance, current 3 amps. Okay, so suppose this is 3 amps. Okay, so this is 3 amps, and here this is also 3 amps. Okay, now take the voltage corresponding to 3 amps for the diode. Okay, now 3 amps means that we're talking about positive current, and when the current is positive, diode behaves like a short circuit. And it's clear from here, when we're talking about 3 amps, the corresponding voltage is 0. Okay, VD is 0. And then, when the current is 3 amps, the corresponding voltage for the resistor is this amount here. Okay, therefore, 0 voltage from here, and this amount we are here. So that gives us this operating point for 3 amps. Okay. And then pick another current. Let's say 1 amp. For 1 amp, again, it's a positive current. The corresponding voltage is 0 for the diode. The corresponding voltage is here, something for the R times corresponding voltage is R times I. Okay, for the resistor, and 0 plus that amount of voltage gives us the voltage for the overall curve. Okay? So it's clear that we don't have to go through all those intermediate points. It's clear that when the current is positive, the IV characteristics will imitate the IV characteristics of the resistor. Okay? Which makes sense because when the current is positive, this is a short circuit, therefore we can ignore it. It's just a line. Therefore, the overall IV characteristics simply obeys Ohm's law. So what we have is, therefore, for positive current, we have this constant slope, and the slope is the conductance of the resistor. So here we have 1 more R. Now we go to negative currents. We get current, okay, let's say minus 12 amps. For minus 12 amps, we have this amount of voltage coming from the resistor, okay? And for ideal diode, for minus 12 amps, we have nothing because diode doesn't allow negative currents, okay? So how we do the addition in that case? Well, there's one way that simplifies this operation, okay? And that one way is you non-idealize the diode, okay? So here the diode for negative voltages, it has 0 slope, okay? Instead of 0 slope, you give it a very tiny but positive slope, okay? So instead of taking this as the tail of the diode, what you do is you suppose that it has not 0 but very small slope, okay? If that is the case, then for minus 12 amps, you will obtain some voltage. Because the slope is very small, this voltage will be very large, magnitude-wise. So this very large voltage plus this moderate amount of voltage will give you a very large voltage, okay? And then you do the same thing for some other current, let's say minus 100 amps. For minus 100 amps, we have something here, some moderate voltage coming from the resistor, and from the diode, or the non-idealized diode, we have some enormous voltage, and if you sum the two up, we have a very large voltage. So what happens is, with non-idealized diode, the tail is something like this, for the overall IV curve. Now you make your diode more and more ideal by moving this tail closer and closer to the horizontal axis. As you move this tail closer and closer to the horizontal axis, clearly the tail here in the overall IV characteristics becomes closer and closer to the horizontal axis, and in the limit, what happens is you reach the horizontal axis, okay? Therefore, that's the answer. Okay? That means the ideal, this one port does not allow any negative currents. Okay? Now let's do almost the same thing, this time with diode put in the opposite direction. Plus, minus, V again. This is I, this is the resistance, this is VR, and plus minus, this time this is VD. Okay? Again, we have V equals VR plus VD. Okay. The diode IV curve, the resistor IV curve, again, we're adding them in series summation, and this is the resulting curve VR. Okay. Now, as before, we have the same IV curve for the resistor. This is V, R, this is I, this is the origin. Now, as for the ideal diode, now the diode is reversed, the terms are reversed. Remember this fact here. If you reverse the terminals, then what you do is you take the set of operating points and you take their reflections with respect to the origin. Okay, so this part moves here, and this tail moves over there. So we're talking about the following set of points on the IV plane. Okay? And now this IV curve and that IV curve added in series addition results in what? Pick a current. This time negative currents are allowed, but negative currents are allowed, but positive currents are not allowed. For negative current, let's pick minus 10 amps. The voltage, corresponding voltage, VD is 0, and then corresponding voltage for the resistor is this amount, and then 0 plus that amount is the same amount here, okay? So, and then pick another one, minus 5 amps. The corresponding voltage is 0 for the diode. Corresponding voltage is here, this amount for the resistor. This amount plus 0 gives you this amount, okay? Therefore, the tail of the overall IV curve will imitate the tail, will imitate the resistor when the current is negative, okay, or when the voltage is negative. And this time, this guy does not allow positive currents, okay. Again, with a trick that we did here, instead of considering this as flat, you consider that it has some very tiny but positive slope, and then pick a current, okay, 13 amps. For 13 amps, since the slope here is very tiny, the corresponding voltage will be very large. Okay? And then that very large voltage plus this moderate amount of voltage will give you something very large. And what happens is, with the non-idealized diode, you have a tail like that. And as you make your non-ideal diode more and more ideal, this tail becomes closer and closer to the horizontal axis, and in the limit, it snaps onto the horizontal axis, meaning that all these points with positive voltage and 0 current are your operating point. Okay. Here we have one graph. Okay. Now let's move on to some other examples. This time, let's consider parallel connection. Okay, this is our one port that we obtained by combining an IB diode with an LTI resistor in parallel. This is the current, and this here is the voltage of our one port. Okay. Now, since these guys are in parallel connection, they share the same voltage, and that voltage is V. Okay, so VD and VR is the same, and we are denoting it by V. As for currents, they're independent. So this is ID, and here this is IR. Okay, and clearly I equals IR plus ID. So what we're going to do now is for addition is we're going to plot the IV curve for the diode, we're going to plot the IV curve for the resistor, and then we're going to perform parallel addition. And by parallel addition, what we mean is you pick a voltage, okay, and figure out what current that voltage generates for the diode and what current that voltage generates for the resistor, and then those two currents, and that's corresponding current for the overall one port. Okay, so let's do that. VI equals V, okay, this is I, diode, this is I. Resistor. Okay. Now the IV characteristic for the diode is this here and the vertical positive axis. Okay. For the resistor, we have Ohm's law, so the slope is 1 over R. Okay, slope is the conductance. And now, what we are performing is we're performing parallel addition, okay, of those two curves. Now, parallel addition means what? Just choose a voltage, okay, and then figure out the current for the diode, figure out the current for the resistor corresponding to that particular voltage, and add those two currents, and you obtain the corresponding operating point for that voltage. Okay, let's choose minus 12 volts, let's say. Okay, minus 12 and minus 12. So for minus 12 volts, what's the corresponding current for the diode? Corresponding current is 0. For minus 12 volts, the corresponding current is this amount here for the resistor. Therefore, 0 plus that amount gives us this amount, okay, same as here for the overall 1 volt. Choose another voltage, minus 3 volts. Minus 3 volts gives you 0 current for the diode. Minus 3 volts gives you this amount from the resistor. Therefore, 0 plus that amount is that amount for the overall 1 volt. Therefore, whenever the voltage is negative, the overall IV curve will imitate the LTI resistor, meaning that for negative voltages or negative currents, the tail will have the slope that equals the conductance of the resistor 1 over R. Okay. Now, how about positive voltages? Okay. Let's pick a positive voltage, plus 5 volts. Now, this diode doesn't allow positive voltages, okay? But no trading points on the right half plane. So what we do is we non-idealize our diode. The trick that we use here, by non-idealizing, i.e. instead of considering this slope to be infinity, we consider a very large but finite slope. Okay, so it will be something like this. And now for 3 volts, let's say, we have this amount of voltage coming from the resistor, and since the slope is very high but finite, we will have some very large voltage coming from the non-idealized, okay, diode. This very large current plus this moderate amount of current will give you some very large current in the overall curve. You go to another voltage, let's say 100 volts. 100 volts will give you even a larger current, a very, very large current, because this slope is very high. And then from here you obtain some moderate current. Add those two currents, a very large current plus a moderate current gives you a very large current. Therefore, the corresponding operating point will be with a very large current value. Therefore, the overall thing will look like this. Okay. Now what you do is you make your non-ideal diode closer and closer to ideal by making this slope larger and larger, okay, approaching infinity. As this slope becomes larger and larger, this slope in the overall curve becomes larger and larger, and in the limit it snaps onto this vertical axis. And therefore this is the overall IV curve for the parallel connection. That means this one port does not allow positive voltages. So what we did here is we added currents. Now let's do another thing. Consider this time have a resistor and a diode in parallel, and to that we have another resistor connected in series. This is the overall current, and here this is how we polarize our voltage V. And what we have is, for R1 and R2, we have these voltages. This is V1, and this voltage here is V2. Now, if we know the IV characteristics of this thing as a one port and this LTI resistor R2, then we can simply perform a series addition to obtain the overall IV characteristics of this one. Okay. Now, the IV characteristics for this one port here is I versus V1, and we almost already did this. Okay, we have a very similar topology here. The only difference is that the diode is pointing down in that one port, and now the diode is pointing up. And now transition from that component to this component is easy. All we have to do is just rotate 180 degrees. That is, you're swapping the terminals. Swapping the terminals would mean, for the IV curve, you're taking the operating point's reflection with respect to the origin. Therefore, the IV curve for this one port is simply this. Okay. The slope here is the conductance of the first resistor, 1/R. And now we're adding in series this curve, and this curve corresponds to just a simple single resistor. Therefore, the slope will be 1/R2, and the overall IV curve is here. Now let's figure it out. Okay. Now, for what we're doing is we're adding voltages. Okay. So V equals V1 plus V2. So what we do is we pick a current, okay, and figure out the voltage coming from that particular current, and figure out the voltage V2 coming from that particular current. Add V1 and V2, and the resulting voltage you mark on the overall IV curve. Okay. Pick a current, okay, minus 5 amps. Pick a current, same current, minus 5 amps. From here, V1 is 0, no voltage contribution coming from this one port, and here we have this voltage, this amount of contribution of voltage, and 0 plus this amount is clearly this amount. Therefore, the corresponding voltage for minus 5 amps is marked with this point. Choose another negative current, okay, minus 1 amp. Here again you have no contribution, 0 voltage. Here you have this amount of voltage, okay, 0 plus this amount gives you that amount. Therefore, it's clear that we have for negative currents, the tail imitates the tail of the second component, okay, second resistor. Here this voltage is 1/R2. Okay. Now for positive currents, okay. For positive current, we have some non-zero contribution from the first one port, and we have also non-zero contribution from the second component. This plus that gives you something a little bit larger for the overall voltage. And then pick another current. From here we have this amount of contribution. From here we have this amount of contribution. V1 plus V2 gives you something a little bit larger than both V1 and V2, and therefore what happens is here we have the curve that's closer to the horizontal axis than this tail or that tail. Okay. Now the question is, what's the slope of that tail corresponding to positive currents or positive voltages? So what we have is I equals V1 over R1. Okay, when we're talking about positive currents, the relation between V1 and I is V1 is R1 times I. Likewise, here we have V2 over R2. Okay, for positive currents. Therefore, the slope, the ratio of I to V when the current is positive is I over V1 plus V2, because V is V1 plus V2. And V1 is R1I, V2 is R2I, therefore we have I over R1I plus R2I. And the i's will cancel, and we have 1 over R1 plus R2. Therefore the slope here must be 1 over R1 plus R2. Okay. It's also easy to see from this circuit. For positive currents or for positive voltages, this will behave like an open this will behave like an open circuit. When this is an open circuit, we have R1 and R2 connected in series, therefore the resulting resistance will be R1 plus R2. Therefore, the conductance, which is the slope, is 1 over R1 plus R2. Okay. How about the next example? Then we have this one port for which we know direct characteristics and an LTI resistor connected in parallel. Okay, so let this be R1, let this be R2. This is the overall current I. This is the voltage V, and let's divide the current as I1 for here and I2 here. Okay, clearly I equals I1 plus I2, and the voltage is same for both components because they are in a parallel connection. Okay. Again, let's draw separate IV curves, and by summing them up, you obtain the overall IV characteristics. V versus I1, V versus I2, and here we have V versus I, where I is I1 plus I2. Okay. Now let's V versus I1. You already obtained it in our earlier analysis, and it's this. The slope is 1 over R1. For the second component, it's just a resistor, therefore it's a line passing through the origin with slope equals conductance 1 over R2. And now what we're doing is we're doing parallel addition. Okay. Now let's figure out the resulting curve. Parallel addition means that pick a voltage, figure out the corresponding currents, and add those currents to figure out the resulting current in the overall one port. Okay. Okay, pick a voltage, something negative. The current contribution, I1, is 0. The current contribution for the second component is this much. 0 plus that much is this much. Okay. Pick another negative current, minus 1/2 amps, let's say. The corresponding, pick another voltage. The corresponding current for I1 is 0. The corresponding current for I2 is this amount. 0 plus that amount is this amount. Therefore, for negative voltages, the tail will have the slope equals 1 over R2 to indicate the resistor. For positive voltages, pick a positive voltage, okay, 6 volts. Here we have the contribution coming from the first component. For the same voltage, here we have the contribution coming from the second component. This contribution plus that contribution gives us something a little bit larger than both contributions. Okay? And then the overall tail will be steeper than both this tail and that tail, and the slope will simply be the sum of individual slopes or sum of conductances. So here the slope is 1 over R1 plus 1 over R2. Okay. So far we have not introduced constant sources. Now let's see a few examples where we also have in our one port a constant current source or a constant voltage source, a battery. Okay. Consider, for instance, a diode connected in series with a constant voltage source. Okay. Plus, minus, V. This is I. This is VD, the voltage of the diode. And here we have some, suppose it's positive, some voltage E. Okay, and V is clearly VD, voltage of the diode, plus this constant E. That's, you can take 12 volts, for instance. Okay. So let's do series addition. We have VD versus I. We have the source, V source versus I. And then we have the overall IV curve. Okay. This is this curve here. And this for the source or the battery. Regardless of the, by definition, regardless of the current passing through it, it always provides E volts across its terminals. So therefore, that's the IV curve for the source. Now what we're doing is we're performing series addition of those two curves, and the result is, okay, the result is you take here the curve and move everything E units to the right. Okay. Or again, you can do the analysis that we did, the trick that we did for the previous one course, for instance. Pick a current, and for each of those currents, figure out VE, figure out E. Well, there's nothing to figure out with E because it's constant, and then add those two voltages, VD plus E, and that gives you the overall voltage. Okay. For instance, pick a current, a positive current. Okay. Corresponding voltage is 0 for the diode, and this amount for the voltage source. Therefore, for the overall component, we have voltage equals E. Okay, another positive current. Okay, the contribution, voltage contribution is 0 from the diode. Voltage contribution is constant. It's E from the source. Therefore, 0 plus E gives you E. Therefore, for all positive currents, the operating points will all have the same voltage, and that voltage is voltage of the voltage source E. Now, what happens with negative currents? Okay, pick a negative current. Okay, again, here we have some voltage E, but here there's no corresponding voltage. So what we do is we do the regular trick. That is, we now idealize our diode, and what happens is instead of considering this slope to be 0, we consider something very, very tiny. Something like that. So pick now, again, a negative current. From here we have E. From here we have something very large with magnitude and negative sign. From this very large magnitude, plus E will give you something very large with negative sign. So what happens is, the sum is something like that, where we're summing a non-ideal diode with a constant source. And as you make your diode more and more closer to ideal, that is, as you make this tail flatter and flatter, this guy will become closer and closer to the horizontal axis. And therefore the overall IB curve will be this. Okay. That is, this component never allows for negative currents. Right. And let's consider one with a current source. We have the current source I, and this is I, this is me, and let's call this voltage ID. Again, these two components are in parallel connection, therefore they have the same voltage, which we denoted by V. As for the current of the overall one port, it simply equals the current of the diode ID plus the current of the source, which is constant I. So let's draw IB curves separately and perform parallel addition. Okay. V. Okay. This is ID. This is I source, and this is the overall current, which is ID plus I source. And what we're doing is we're performing parallel addition. Now this diode, the direction of the diode opposes the direction of the current, therefore this is the ID curve. And then as for the source, it always provides the current I, suppose I is positive, regardless of the voltage, and therefore we're talking about this constant current line, a horizontal line at I. Okay, and then we have on the right hand side overall IB characteristics. Okay. Now here, what this did, that the voltage source did in series connection, is it took everything and moved E units to the right. Okay? And here we will have the dual thing, because we have parallel connection. Now the motion will be in the upward, downward direction. And this guy, this source, will take everything here and move up I units. Okay? Therefore, this is the overall curve. This is at I, this is 0 for the one port given here. Okay. And finally, let's consider one port that contains both a current source and a voltage source. Let this be V1, and let this be V2. And here we have minus plus E. Suppose that E is positive. And also suppose I is positive. And we're interested in the IV characteristics for this 1/4, which contains a diode, an constant independent current source, and a constant independent voltage source. Okay. Now it's not difficult to see from the previous example what the IV curve should be for the upper half of our 1 port. A diode connected in parallel with the current source. Okay. V1 versus I, it will be something like this. Okay. Then to this, we're adding through series addition this voltage source V2 and V2I0. V2 always equals minus E, because the polarity of V2 and polarity of battery plus minus, they are opposed one another, and we said E is positive, therefore we're talking about this curve here at minus E. And then this IV curve and that IV curve added in series would result in the following. Here we have a constant voltage source added to something. What it will do is it will move everything E units to the left. Okay. Therefore, the resulting IV curve will be VI0. These points move E units to the left. Hence, we have such shape. And this corner corresponds to I and minus E for the current and the voltage.